All right, we are going to go ahead and get started. Our speaker today is Dr. Judah Cohen, who is the Director of Seasonal Forecasting at AER. He's also a visiting scientist at MIT's Parsons Lab in the Civil and Environmental Engineering Department. If you're at all active on the climate world and Twitter, you've probably seen his tweets. He's very well known for his weekly blog on the Arctic Oscillation and the polar vortex. It's also very convenient that we scheduled this webinar months ago, and it seems like there's starting to be some activity in the stratosphere, and he's been kind enough to add all of this in at the end of his talk. So we will get to all that. But I will go ahead and turn it over to Judah, and we'll take all the questions at the end.
All right, thank you very much, Megan. Hope everybody hears me okay. So it's a pleasure to speak to you today. I'm a winter weather enthusiast, so I don't know, maybe most people don't want to go visit or live in a place like Bismarck, but I would love to be there, especially probably in the month of January. It'd be my favorite time to visit, so maybe an opportunity in the future. I'm going to speak about my kind of my methodology in making winter forecasting. I think maybe the interest is mostly in has to do with the stratospheric polar vortex, but at least the framework of my talk is around the Eurasian snow cover, because really everything that I've come to understand about winter weather and climate dynamics, started with the Eurasian snow cover, but it very strongly involves the polar vortex. All right, so let's see. Okay, so my outline of my talk today. I'm going to develop a 6-step process, how snow cover extent influences winter climate. I'll then bring in sea ice, because I think they work in tandem a bit, and how that also influences winter weather. Then I'm going to kind of segue a little bit into climate change, how maybe Arctic amplification is the accelerated Arctic warming. But that has led to sea ice decline, but also increasing fall snow cover. That's a surprising result. And these two trends are favorable for disrupting the polar vortex. And I'll talk about trends in the polar vortex in the talk, towards the end of the talk. Discuss a little bit last winter, and of course the upcoming winter and the polar vortex. Okay, so I really like this quote. It's hard to make predictions, especially about the future, and it's been attributed to two very different people, Yogi Berra and Niels Bohr. I'm not sure which one, but I do really like the quote. So we're like making forecasts, weather forecasts. We have different time horizons. We have the short range. There, the skill is quite good. There's a cursor. That's like the 1 day to 2 week type forecast, and of course we're really good in the first few days, and then that quickly drops off maybe once we get beyond 5 days to a week. Then we have the seasonal forecast, which doesn't have as good skill or accuracy, but and I think over really the course of my career, I don't think there's been much improvement in that. It's been kind of a stubborn nut to crack. It's been very challenging. And then the one in between. So seasonal is 3 months here, so maybe beyond a month to 3 months, out to 6 months, and then in between those two time frames, time horizon, we have the subseasonal forecast, beyond 2 weeks, or maybe up to about 6 weeks or so, and that actually has the lowest skill of all. Here, maybe the seasonal forecast can capitalize somewhat on these slowly varying boundary conditions, the most well-known being ENSO, and kind of, though recently it seems like the holy grail of long-range forecasting is trying to improve the subseasonal forecasting. It's a bit of an old plot, but I think qualitatively, I think the picture represents state of the art here and these long range forecasts, so seasonal forecasts, and really, can we make a begs the question, can we make a seasonal forecast that the public should care about? Here's the ECMWF, considered the best model that exists currently, and So blue shading is good, is skillful and it's accurate, and then these yellows and oranges are zero or even negative skill. So here's the ENSO region in the Eastern Equatorial Pacific. So here the models have very good skill, very high skill, very high accuracy, but and maybe that good skill extends throughout the tropics. Once you get into the extratropics, so mid-latitudes, high latitudes, the skill really drops off. Ironically, for the ECMWF, they're out of Europe. I guess this is their mission, is to forecast Europe, and their skill is actually worse on the whole globe is for Europe. So a bit of irony there. But again, I think a bit of an old plot, and I do think the qualitative is representative of the current state of the art of technology. And don't need to look backward more than last winter. Here was the NOAA's forecast for this DJF. I kind of showed both deterministic and probability. His for January, February, March. So this kind of was that we had an El Nino, and they had this canonical El Nino pattern, warm to the northwest, cold to the southeast. And as you can see here on the right are the observations, and pretty much completely opposite of what was predicted. I mean, it's really hard to imagine a worse forecast. Yeah, I mean, almost a negative one correlation. So don't have to go far to get examples of that. Certainly, there improvement. There's quite a bit of improvement still, possible in these long-range forecasting. And just to come back to this ENSO. So here's a correlation of ENSO with temperatures across the northern hemisphere. So here's Western North America. So get that kind of canonical pattern of warm northwestern North America, and then cooler. The shading is statistically significant, not very statistically, but cooler here in the southeast. And here's from the North American multi-model ensemble, which is being used for seasonal forecasting and now also subseasonal forecasting. It very much matches this pattern from ENSO. Certainly the warm northwest North America, cooler, that's more like normal here southeast, and then maybe some warming Eurasia. But I mean, outside North America, you really get into just kind of a global warming signal where it's just warm everywhere. And here's more dynamical models. Here's that again, North American multi-model ensemble. Very, very good consistency among the models. Here's your kind of European models mostly. Here's the CFS, NOAA's model. So we use a statistical model that's based on snow cover, a little bit of sea ice. That's been hard to capture in the model. And here was what is observed. So the dynamical models really missed the whole pattern across North America. Also missed, again, it wasn't cold. It wasn't warm everywhere in Eurasia. There was some cold regions. I think here our model did a better job, a statistical model, not a dynamical model like these other three. I thought, pretty good job in North America, though clearly over-predicted the cold across Eurasia. And that was from last winter here again, similar thing from 2 winters ago. Here are the dynamical models, the NMME. Here's the European models. This is December, January, February. Here's January, February, March. Not much change. We had a La Nina, so it was more kind of cold northwest, warm southeast North America. But again, that whole Eurasia again is warm everywhere, universal warmth across Eurasia. And again, here was our statistical model. Here was what observed. So I think, again, certainly across the hemisphere, did a much better job. Even North America, the statistical model showed that cold extending further east than the dynamical models. Well, I mean, not all the dynamical models had it, but that was that. The Europeans missed it completely. Anyway, but again, the dynamical have not been doing a good job, certainly over the past 2 winters. So now, just some background material for my talk. I'm going to talk a lot about the Arctic oscillation. assume most of you are familiar with it, but just can't hurt to bring up. So here's on the right is the mean sea level pressure for the winter months, December, January, February, December, January, and February. Excuse me there. So there are three major players in the northern hemisphere, or winter circulation. There's areas of low pressure in the ocean basin. So there's the Icelandic low in the North Atlantic, and then there's the Aleutian low in the North Pacific, and then there's really only one high pressure, and that's the Siberian high. Focus over the Eurasian continent, maybe centered over Mongolia. A lot of this is topographically driven. And then the first mode of variability is called the Arctic Oscillation. It's strongly related to North Atlantic Oscillation. And you can see it's this tripole. So you have one anomaly centered over the Arctic, or maybe towards the North Atlantic, more in the North Atlantic. And then there's a second, there are two other anomaly centers in the ocean basins themselves, in the North Atlantic and North Pacific. The North Atlantic one is stronger, and this coupling of maybe, so when the Arctic Oscillation is negative, this red would represent high pressure over the Arctic and low pressure in the North Atlantic and the North Pacific. And when the Arctic Oscillation is positive, this would be low pressure in the Arctic and high pressure, again, high pressure anomalies, low pressure anomalies. So you'd have a high pressure anomaly in the North Atlantic and the North Pacific, but definitely is stronger. The variability is stronger here in the North Atlantic, and that does also resemble the North Atlantic Oscillation with pressure anomalies near Iceland and Greenland, and the opposite pressure anomaly near the Azores or Portugal. Okay, it always seemed to me that this mode of variability, this Arctic Oscillation, this dominant mode of variability in the Northern Hemisphere, kind of looks like whether there's an expansion or contraction of the Siberian high. So when the Arctic Oscillation is negative and this is high pressure Arctic, it always seemed to me this is just an expansion northward of the Siberian high, and that suppresses the low pressure systems in the oceans further south. And then when you have a positive Arctic Oscillation, that's a contraction of the Siberian high. The Siberian high retreats or is very weak, and that allows these low pressures to expand northward. Okay. So, very beginning of my career, I found this correlation between fall snow cover and winter geopotential heights here at 500 millibars, and hopefully it looks to you like the Arctic Oscillation. We have one signed anomaly over the Arctic basin, and then opposite sign anomalies in the both North Atlantic and North Pacific basins. Right. So if snow cover is high, you get high pressure over the Arctic and low pressure in the ocean basins. And if snow cover is low, this would be low pressure in the Arctic and high pressure in the ocean basins. And so recently there was a review paper, I'm just addressing it, that said, well, when I did my work in the late 90s, the correlation was really high back then. It was very kind of an opportunistic time to find this correlation, but since then the correlation has really dropped off, especially the most recent period. So do we want to address it? So here's actually a plot of so I've been talking about fall snow cover, but really October is the key month. So it's October, Eurasian snow cover extent, right? And winter, here's the winter Arctic Oscillation. It's going back to, so snow cover extent has been available from satellite data since the late 1960s, but there's even some proxy data that can bring it back to the earlier than that. And so the correlation was quite good, well, throughout the whole period. This is right through this last winter. The correlation 0.35, 99% statistically significant. But you can see that though, really since 2000, after 2012, they've really gone their separate ways. So what is that? A lot of people say, well, okay, the snow cover extent maybe, and the correlation between snow cover extent and the AO was just a random one. I mean, I don't agree with that. But definitely something strange has happened, and but clearly that relationship is, at least over the past, and this is with AO. It's nothing that again, the AO is just some kind of statistic, It has no physical meaning, but even with the temperatures, that this correlation has dropped off. So, but so that's definitely an outstanding issue. I guess, that I'm not going to really address in this talk. So here it is. I just wanted to highlight that. Okay, so early on, our thinking was pretty simplistic. Like I say, Siberia is the refrigerator of the northern hemisphere. And often when we get these cold air outbreaks, people call it the Siberian Express. But the thinking was, we first found this relationship and trying to find the physical mechanism to explain it. That you have this, let's say, snow cover. It really makes this great expansion across Siberia in October. So you have more rapidly expanding snow cover in the month of October. This, snow cover is the highest albedo, the highest reflecting surface, naturally occurring reflective surface. So you have more snow, it reflects more sunlight. That leads to colder temperatures. You build up these cold, dense air masses, and you have a more rapid development of the Siberian high. The cold, dense air wants to spread out. It's blocked to the south and east by the high topographical barriers in Asia. The best known is Tibetan Plateau, but there is a lot of high topography throughout East Central and East Asia. So this cold, dense air, it's easier to spread either over the pole into North America or spread west into Europe. And we get something similar here with the Rockies, right? The cold air, these Arctic outbreaks tend to be east of the Rockies. So you have this cold air coming over the pole, building this Arctic high pressure, strengthening, developing a Canadian high, and getting maybe this positive PNA pattern across the North America, troughing near the Aleutians, ridging along the west coast of North America, and then a trough in the eastern U.S. And kind of the door is open now to these Arctic outbreaks, and you have this northwesterly flow that delivers the cold air from the Arctic into the low 48 of the United States. And then if you had less snow cover, you have less reflectivity. The Siberian high is weaker, develops later. You have low pressure over the Arctic. You maybe have now a negative PNA, negative Pacific North American pattern with ridging near the Aleutians, troughing in the western North America, and then the southeast ridge with southwestly flow across East U.S. and maybe some cold air, though, in the western part of the country. So, that was our thinking, kind of keep it on the other surface, but we quickly came to understand that that was over simplistic, and really not, it's not a two-dimensional problem, it's really a three-dimensional problem, and there's a vertical component to it. And really, this six-step process that we developed, early on in our research, this hasn't really changed much, now close to 2 decades of thinking. So the 6 steps. The first one is the advance of snow cover. So again, October is a key month. That's when snow cover has its greatest variability, and but it can expand the fastest across the Eurasian continent. It's really focused over Siberia. The second step is, so let's say that I'm going to talk about when you have high snow cover and forces a cold signal across the northern hemisphere. You have the rapid advance of snow cover. This leads to colder conditions across Siberia. You have an earlier and more strengthened development of the Siberian high. So it starts out kind of this regional perturbation, but that then triggers or sets off this vertical energy transfer, and you have transfer of energy from the troposphere into the stratosphere. So that when you have the stratosphere absorbing this energy, or you have this northward transport of heat into the polar stratosphere, you get what's referred to as southern stratospheric warming. The stratospheric polar vortex weakens. That's the fourth step. Then the fifth step is this downward propagation. So when you have this heating of the polar stratosphere, the southern stratospheric warming, you have high pressure over the Arctic, you have a low pressure force further south and across the mid-latitudes. So you have an equatorward shifted jet stream, and those circulation anomalies, or here would be the winds around the polar night jet. It's not the jet stream level, but the jet that's in the polar stratosphere is maybe shifted equatorward, and those circulation anomalies associated with the southern stratosphere warming would propagate down I mean, fifth step takes about 2 weeks typically, and then you get to makes it all the way to the surface, and you get this same circulation of high pressure over the Arctic, low pressure in the ocean basins, and the equatorward shifted jet stream, and that all projects onto this negative Arctic oscillation. And this pattern is associated or more favorable for more frequent colder outbreaks, and also with the jet stream south, maybe more snowstorms as well. And, I described it for the positive snow cover case and negative AO, but it's kind of a linear, and it works both ways. Just the opposite if you have less snow cover leading to a positive AO and milder conditions across the northern hemisphere. So kind of support this six-step process, I'm going to compare and contrast two different winters. The first one is 1980 and 89, where we had low October snow cover and a strongly positive winter AO, and the other one is 2009-10, which is high October snow cover and a strongly negative AO. Okay, so here just an animation quickly of the snow cover expands. So here's Siberia, on the bottom here of the slide, and as you can compare that in 2009 the snow cover expanded more rapidly in 2009 compared to 1988. Okay, so that's the first step. So you have this variability in snow cover, and again, the thinking is that large changes in snow cover extent can really impact the Earth's energy balance. I'm sure this is something that you guys are well aware of. Where not only do you have high albedo, but also the insulating properties of snow cover, which decouples the atmosphere from this heat that's in the ground. Okay, so now remember, we're going to address that six-step process. So the first thing was that that kind of regional perturbation, that it changes in the Siberian high. So low snow cover, so 1980 we had low snow cover, maybe warmer temperatures, and we expect low pressure. And the key area which really comes out is northwest of the Siberian high. So the Siberian high is kind of more, the center is more towards Mongolia, that's where it's centered. You would look for what happens northwest of there towards the Urals and Scandinavia. So this again, so we could see blues, throughout my these talk will be negative anomalies or low pressure in this case, and red positive anomalies or high pressure. So you can see this northwestward of the Siberian high, you have low pressure anomalies. And what actually starts out as a regional perturbation in the fall, as you get into the winter, you can see here very nicely, you get this low pressure encompasses the entire Arctic basin, and you have the opposite anomalies in the ocean basin. You get this really nice canonical AO, but it all starts out as a regional perturbation. And contrast that with what happened in 2009. This what's what happens after October, and you have the snow cover. It's nice seeing this expand, positive sea pressure anomalies northwest of the Siberian high, the high Siberian high center. Right? It's northwest expansion, and then what started as regional really becomes a hemispheric pattern with positive sea pressure anomalies across the high latitudes and low pressure anomalies in the mid latitudes, especially in the ocean basins, and this high pressure over the Arctic. So again, you have high snow cover, and then you have this expansion of the Siberian high to the northwest. Low snow cover, you don't have that northwest expansion. And also looking at temperatures, the same thing. And here's really just to show you this kind of go from a regional perturbation to a hemispheric. So you have low snow cover, and you can see in Siberia responds with positive temperature anomalies, relatively warm temperatures, but it starts out kind of isolated to Siberia. Over, as we get into the winter months, you'll see it's expanding west into Europe. There's warm anomalies, and then even across the pole into eastern North America. So this kind of with this regional perturbation of warm temperatures expands, right, and west into Europe, and even north over the north into the U.S. And then to contrast that, here's 2009. So it started out warm in the fall, but then you have this rapid expansion of snow cover. You can see the temperatures respond. It's cold, and the cold is really limited or isolated to Siberia. It's warm elsewhere in the hemisphere, but as we get into the winter months, you're going to see that cold expand. You can see it expanding to North America, and you can see it expanding west into Europe. And this is really the kind of the canonical AO pattern that you see. I'm going to show that later. But so again, this regional response that happens in Siberia is then kind of mimicked or imitated elsewhere in the hemisphere. Skip the slide. I do want to focus on this because, again, getting into the whole stratosphere and prediction of what might happen. I mean, the key is, this is a figure of mine that it came out paper in 2014, so it's a little bit complicated, but I think it's a really important figure and pretty striking. So it regresses October Eurasian snow cover extent index right onto sea level pressure, and so that's the contours. And so when snow cover is high, you get these positive sea level pressure anomalies. It's the Urals and Scandinavia, and you get the opposite negative anomalies in the ocean basins. Let's see, this thing put in the dash might have been easier to see than positive. And then you have the other thing that's being regressed, the regression is the December polar heat flux at 100 hectopascal. So that's in the lower stratosphere. That's the northward transport of heat. And that's, when you get a sun stratospheric warming, you have above normal northward transport of heat. It kind of makes sense. And then you have a strong vortex that would have less than normal polar transfer of heat. So December tends to be an active month for this polar heat transport. And that would, so the polar heat flux, polar heat flux, in December was a very good indication of what would be the behavior of the polar vortex in January of the next month. So there's a lot of heat flux in December. You tend to get a sun stratospheric warming, in January. If you have less than normal, then you tend to have a strong polar vortex. When you regress that value, this December heat flux in the lower stratosphere, again with November sea level pressure, and you get the same, almost the same exact pattern. You get this high pressure. So when you have a above normal polar heat flux, and it would lead to a weaker vortex, polar vortex, you have high pressure over the Urals and the Scandinavian region, and you have low pressure in the ocean basins, and that's the contour, that's the shading, right? That's the shading. And then you have less than below normal polar heat flux. This would be low pressure in the Urals and Scandinavia, and have higher pressure in ocean basins. And that would lead you to a stronger polar vortex. But again, I think it's really quite striking, the common pattern here. The correlation is somewhere around 0.9 pattern correlation, so really high. And if you do other variables, you would not get this really nice match. Okay, that was a little bit of a digression. Okay, so now moving on. So first step was snow cover. Second step was this either expansion or contraction to the northwest, the Siberian High, and then the third step is the polar heat flux, or we'll call it wave activity flux. So again, in 88, the fall of 88, you had low snow cover, you had a weaker than normal Siberian High, and you can see you have a deficit in this polar heat flux. The blues show negative anomalies. Here's the kind of up here is the polar stratosphere. So you can certainly see the blues. This accumulation of this energy deficit. And then actually at the very end of the winter, there was a sun stratospheric warming toward the very end. In contrast, in 2009, you have the high snow cover, you have this northwest expansion of the Siberian High, and you can see the reds represent you have above normal or above normal polar heat flux in the polar stratosphere. Again, so the polar stratosphere, let's say it would be around in this region here, but you see it's reds, and certainly contrasts very nicely with 1988, where it's dominated by the blues, or this deficit of polar heat flux. Now moving on to the next step, I think this is again, this is the polar stratosphere. There's an animation of the polar vortex. And you can see it starts out, the blues are cold temperature, here's the polar vortex, and right over the pole it starts out nice and strong. Actually, this winter it's going to stay strong. So this is 1980. We have low snow cover, a contraction of a weaker than normal Siberian high, less than normal polar heat flux. So the polar vortex, is going to be relatively strong. It bounces down a bit, but in most part it stays intact. So the blues are the cold temperature, these oranges and yellows are warmer temperatures. So you see the cold stays confined to the Arctic, and the warmer temperatures are on the periphery of the polar vortex, mostly in the mid-latitudes. So it's quite striking, the difference if you look at 2009-10. So it starts out similar, you get a strong vortex, but then warm air is going to come out of Siberia and rush into the Arctic region and knock the polar vortex off the pole. So you have this much warmer temperatures invading the Arctic region, and that cold air that was confined previously over the Arctic now kind of discharges and spills out to lower latitudes. And a very strong mixing of the air masses. And again, this is all in the stratosphere, it's not what's happening in the troposphere. But really quite a dramatic difference between a strong vortex and a weak vortex. Strong vortex where the cold temperatures are really confined over the Arctic, and in a weak vortex we really have a very strong mixing of the masses, exchange of air masses with the warmth invading the Arctic and the cold that was previously confined to the Arctic spilling out to lower latitudes. Okay, so that the fifth step is the downward propagation. I like to use a polar cap to look at that. This is the geopotential heights averaged from 60 north to the pole at all levels from the surface up into the mid-stratosphere. And blue would be low pressure over the Arctic. It's a very good proxy for temperature. I think I might have a slide explaining the polar cap heights, but I should put it here. I think I'm putting it later on. But so the blues mean basically the Arctic region from the surface, to the mid-stratosphere. It's dominated by low pressure. So that was, and then you kind of have this downward propagation of those. So those, again, the circulation arms really start out in the stratosphere and propagate down. Doesn't look maybe as good in these downward propagation, maybe not as easy to see, but in 1989 as it is in 2008. You clearly see here you have this kind of pulsing red of the polar cap height, so large pressure heights, rising pressure, first in the stratosphere, and then that propagates down with time. So it happens here in November, and then reaches the surface in December. There's another event actually that happened later on. Again, there was kind of this downward propagation, but this is the best, I think, most visible. At least from these two examples I'm showing here. So again, in 1989, you have low snow cover, weak Siberian high, less polar heat transport, a stronger polar vortex, it's characterized by low pressure, and then that propagates down to the surface. In 2010, you have high snow cover, strong Siberian high, increased polar heat transport, a weaker polar vortex, and rising heights or pressures over the Arctic region that first starts out in the stratosphere and propagates down to the surface. And that's the fifth step. And what you get, the final sixth step is in 88-89, you get very much a canonical positive AO. This is the sea level pressure anomalies, but the low pressure over the Arctic basin, positive pressure anomalies in both the Atlantic and the North Pacific. And in 2009-10, when you had the high snow cover, increased strength in Siberian high, increased polar heat flux, a sun stratospheric warming or a weaker polar vortex, and then you get this negative AO throughout the winter time, high pressure over the Arctic, low pressure in the Arctic basins. And of course, what's more important to the people is not the pressures, but the temperatures. And you can see in 88-89, you kind of get this canonical AO, positive AO temperature pattern with warm temperature across northern Eurasia and into the eastern U.S., cold temperatures here, Greenland, and in the Mediterranean region. So that's called often the AO pattern is called the quadrupole. So you get warm Europe, cold Mediterranean and North Africa, cold Greenland, and warm Eastern U.S. That's for the positive AO. You get the opposite of negative AO. But in negative, you can see here we had 2009-10 cold temperatures across northern Eurasia, cold temperatures in the Eastern U.S. You can see very nicely that quadrupole, cold Europe, warm North Africa, warm Greenland, northeastern Canada, and very cold southeastern U.S. So kind of just summarizing it, this is a graphic put out by the National Science Foundation. The paper was published, but so here in the timeline on the bottom, you have this fall. Let's say you have increased fall snow cover across Siberia. October is a key month. That leads to this Siberian, expansion, northwestward expansion of the Siberian High. It's often called Ural Scandinavian blocking. Here you see the new jet stream is represented by this ridge over the Urals that increases this vertical energy transfer into the polar vortex, or this polar heat transport, warmth coming up from lower latitudes into the polar stratosphere. We get a polar sun stratus warming or weakening of the polar vortex, or the temperature rises in the polar stratosphere. And then that propagates down to the surface, and you get this equatorward shifted jet stream more. So here's the finale. You get kind of troughing and cold temperatures in the eastern U.S., maybe more snowstorms because the storm track has shifted off the coast, the suppressed south. Similar things happen in Europe. So I mean, but the impacts are focused throughout the North Atlantic Basin. Just this is not really the gist of my talk, but I do want to say that how the models do with representing what I've explained and I've shown with observations. So here's that. So I showed earlier with sea level pressure the regression of snow cover with this is actually now my paper. This is from a paper by my colleague who used to work at AR, but now is at the University of Oklahoma, Jason Furtado. It's not our paper. This is just no mistake there. But here's looking at 500 millibars. So I regressed I showed earlier regression of snow cover, October snow cover with November sea level pressure. Here it's regressed with November 500 millibar heights. And here's the reanalysis. You can see that ridging or Ural blocking, Ural Scandinavian blocking with low pressure in the ocean basins. So similar kind of plot to what we show with sea level pressure. It's 500 millibars. And this is looking at CMIPS models doing that same regression, and you can see it shows no sign of that Ural blocking. Instead of more high pressure in the so with snow cover would give you high pressure in the Arctic. In the models, it shows you low pressure. So very, very different pattern. And the models do not really, I think, simulate this coupling that I've argued using the observations at all. And there's two ways to interpret that. That this any relationship shown with the observations is just a random or by chance. There's nothing physical there, or the models certainly have deficiencies. They're model errors, and they're not coupling correctly what's happening. I believe more in the latter, that is a model deficiency rather than just some random or by chance correlation. And again, just kind of summarizing here, like all these different steps. So here's this wave activity flux, or the pole, so energy transfer, but a very large component of it is this polar heat flux. So here's regression of snow cover with the daily polar heat flux, from the surface through the mid-stratosphere. And you can see here, when you have high snow cover, you tend to have an increase in this polar heat transport from late November and into mid to late December. And then looking at the polar cap heights, again, a very good proxy for, not only is it, but it's a measure of pressure, but it can also be throughout the free atmosphere, be a good proxy for temperature. So in your high snow cover, again, when you have that increased polar heat flux here in November to December, you get this increasing polar cap heights or warming in the polar stratosphere, and then those high heights and warm Arctic kind of pattern propagate down to the surface, and you get kind of this negative, increased polar cap heights, which projects onto the high pressure over the Arctic, which projects onto the Arctic Oscillation. And actually, this is looking at, this is not polar cap, excuse me, this is the Arctic Oscillation Index. But you kind of get this negative AO first in the stratosphere, which propagates down and kind of peaks actually in February. This is a delayed response. And again, just, I mean, one reason I showed that was just to show the difference between the models, and that was daily values, but here's looking at monthly to compare with CMIPS, which also shows in the monthly value. So you can see anywhere either there's some stratospheric warming, negative AO, both in the stratosphere and the troposphere here in January, that shows up when you correlate Eurasian snow cover with this polar cap heights, right? And you see the significant correlations, which are shown by the black lines in December and January. There's nothing, the models show absolutely nothing. There's somewhat of an increase in the heights right at the beginning in October, but there is no relationship whatsoever with the polar cap heights. And that would be also with the AO in the winter months. At least this is the model simulations. Okay, so I talked about snow cover. I mean, the sea ice, I just want to kind of bring it in because I do think it's very important. Here's an early paper, Kim et al. Showing this, that looking at the polar cap heights, if you correlate sea ice, you also get high pressure over the Arctic. With low sea ice gives you high pressure over the Arctic. Warming over the Arctic, which is, let's say for Barents-Kara sea ice, so that bullseye of warming over Barents-Kara seas and low sea ice, and it gives you cold temperatures across, basically mostly over Eurasia, some into North America. But look at this polar cap height, you also get this, what I would call tropospheric stratosphere, tropospheric coupling. You get this initial tropospheric precursor, which tends to be that Euro blocking. That leads to a weakening of the polar vortex and then this downward propagation. This on the left is on the observations. On the right, the model here, this paper says that it can couple this sea ice hemisphere coupling as we, it matches the observations. I'm quite skeptical of it, but at least here in this paper, they show both the observational modeling and this coupling going on. Very similar to what I described as snow cover. And you can actually, if you combine, we did a paper, we looked at both sea ice and snow cover combined. We did this coupled, kind of this multivariate EOF. So we looked at snow cover, the first snow cover, sea ice. You can see the low sea ice here in the Barents-Kara. Well, this is EOF. It's linear, it goes both sides. But let's say we're talking, high snow cover across Siberia, low sea ice in the Barents-Kara Sea, and the dominant mode. And the multivariate with sea level pressure, you can see this very canonical AO pattern with high pressure. So with high snow cover, low sea ice, you get high sea level pressure over the Arctic and low sea level pressure in the ocean basins. And if you're looking at the time series of this multivariate EOF, a very high, strong correlation with the Arctic Oscillation Index. So again, it does seem that high snow cover, low sea ice favors this negative AO. Low snow cover, high sea ice would favor a positive AO. And here's that was for sea level pressure, looking at temperatures. Yes, you get this canonical, you get the same modes, the high snow cover in Siberia, low sea ice. In the Barents-Kara Sea, you get cold temperatures throughout Eurasia, but you also Eastern North America. This for the different months, there's some variability, but really the key takeaway is that you get this very canonical AO pattern. There is difference in timing. It seems like here's correlation of the polar cap height with both Eurasian snow on the top and sea ice on the bottom. It does seem like the impacts of snow cover, is earlier in the winter. Again, this December, January time frame, where the sea ice is more January, February time frame. So, I mean, that's something that seems to come out of my analysis. I did want to show that there does seem to be this different. I mean, you get this weakening of the polar vortex from both high snow cover and low sea ice, but there does seem to be a difference in the timing of the snow cover. The disruption of the polar vortex tends to come earlier. Here's kind of the combined, and you can see just in general you get this high pressure over the Arctic, or the tendency for this negative AO, and you can see this also with the WAF, you tend to get increased polar heat flux with the high snow cover of low sea ice. Again, maybe this is, at this point, just being a dead horse, but again, you get this very similar. Here's looking at the another paper looking at the circulation pattern, but again with sea ice and snow cover, you get the same thing of high pressure, or high snow cover, low sea ice would be high pressure over the Arctic, low pressure in the Arctic Sea ocean basins. And that extends from the surface all the way through the stratosphere. Interesting, I think I'm going to skip that. So what is, again, what is it that, why is both the snow cover and the sea ice so important, and why is it the Barents Kara sea ice per se? That's the key region for sea ice, and Siberia for the snow covers, location, 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 taken borrowed from real estate, right? You look at the long wave pattern across the hemisphere, you get this strong trough in East Asia and this ridging in this across northwest Eurasia, so including Urals and Scandinavia. And if you look at the anomalies, the zonal anomalies in the pattern, you see the strong troughing here in East Asia and this strong ridging across northwest Eurasia. So troughing in northeast Eurasia, ridging in northwest Eurasia, right? So northwest Eurasia, you have the Barents Kara seas is in that region. Low sea ice means heating that amplifies the ridging. Here in Siberia, you have above normal snow cover that leads to cooling that deepens the troughing. So so these stationary waves, which are orographically and thermally forced, can be amplified by these changes in the cryosphere, right? The snow and the sea ice that's been happening. And again, trying to now, kind of again this three-globe explanation, but kind of bringing sea ice into it. In September, you have low sea ice, mostly on the North Pacific side. Now you have kind of like this reverse great lake effect snow, because now the ice is being peeled back. There used to be ice there all the time in the Arctic Ocean. Now it's disappearing. And you have open water. You have, let's say, high pressure over the Arctic that induces a northerly flow, and you have this moisture flux from the Arctic into Siberia, which didn't exist 20 years ago. That leads to an increase in snow cover. Now the sea ice anomalies, they transfer, or they kind of move from the North Pacific side to North Atlantic side into the Barents Kara Sea. That form, that heats the atmosphere, that leads to ridging. So you have this ridging over northwest Eurasia, troughing over northeast Eurasia. That is, again, taking nothing away from my talk, that's favorable for this increase in the vertical wave activity flux, or this polar heat transport into the polar vortex. That leads to a weakening of the polar vortex, warming over the Arctic. You can see here I show the polar vortex stretching and maybe trying to split. And the jet stream does a similar thing in the troposphere, where you have this high pressure and ridging over the Arctic and troughing and cold temperatures over the mid-latitudes, both over Eurasia and North America. But for these, as I'm about to show, we really focus on Eurasia, these type of events. Because I want to bring in Arctic change into this, because I think there's been some interesting trends that were unexpected. So here's I think the temperature anomalies for, I think this is the trend maybe through maybe through last year, 2000, that we have 2018. So obviously a lot of warming throughout the globe, but you can see the high latitudes, that warming is amplified. Right? It's accelerated relative to the rest of the globe. And here's the time series, and used to be much colder. Now they're pretty steady, increasing trend. And of course, with these warmer globe, and then the projections of less snow. There's something what I'm showing here, both from in the media and in publications, and this makes sense, right? Less warmer globe would support less snow. And warmer temperatures also bring extreme weather, and extreme heat, extreme droughts, extreme rainfall. Also, economists think that extreme weather and natural disasters is the biggest global risk to the economy. And, but with global warming, the thing that the scientists, this is from the National Research Council, NRC, or Academy of Sciences, paper, they said the thing they're most confident is a decrease in extreme cold. You would think maybe with global warming, maybe the thing you'd be most confident about is extreme heat, but the decrease in extreme cold is the thing that scientists are most confident will be an impact of global warming. So here's looking at some extreme events across the hemisphere, so both precipitation and temperature. And Here's a time series. So if you look at precipitation, you can see there's been an increasing trend in these extreme precipitation events. This is again what we were projected from global warming. There's an increase in warm temperatures. Here's warm summer months. Again, here's a kind of a two-dimensional look at it. You can see that there's been more locations across the world are experiencing warmer days and heavier precipitation events. But if you're looking again, here's icing days, there's days below freezing or cold winter months. There was kind of something interesting happening with the trend. So there's this, as expected, decreasing trend in cold extremes. But it kind of bottomed out in the 1990s, and then kind of a bit reverse course. So that was kind of an interesting result that I noticed. That it kind of was this. What I'm looking for, but yeah, I mean this reversal. Here in the 1990s, certainly not something that was projected. In the models. Now, I do want to, maybe it's a bit busy, but this is showing September sea ice extent. So another piece of what I like Arctic amplification, I don't think just involves temperatures, but I think it involves the cryosphere, involves the snow and the ice. So here's September sea ice in the blue, and the red is October snow cover. So as expected, the September sea ice extent is decreasing. It's pretty monotonic. Decreasing, putting the trend line there. And then here's that's Eurasian snow cover in October. That was not expected, but it's been a pretty strong increasing trend. And so you have both, with this Arctic amplification, you seem to have both this decreasing sea ice and this increasing snow cover. And the correlation between the two is almost 0.6, a pretty good correlation between the two. Anyway, so you look at the winter temperature trends. This is, go back, let's say to 1960. You get the pattern you would expect. Warming throughout the whole hemisphere. It's amplified in the Arctic region. Here's the zonal mean. You can see there's some slight warming in the tropics and increases in the mid-latitudes, and then really accelerates as you get to the high latitudes. But if you look at the time series, the Arctic and the rest of the hemisphere are separated out. The Arctic being in red, and the rest of the hemisphere in black. You can see that up to about 1990 or so, they were, the trend were similar. They were almost parallel. There's more variability in the Arctic than the rest of the hemisphere, but otherwise the temperature trend was very comparable between the Arctic and the rest of the hemisphere. But then in 1990, there's a clear divergence where the warming accelerated, and there is really no warming in the rest of the hemisphere. If you look at the temperature trend since this divergence, right, which is the really period of defined as the period of Arctic amplification, you get a very surprisingly different temperature trend now. So you still now you have really much more amplified Arctic warming, but now you get these cold temperatures, cooling trends across really strong across Eurasia, but also in North America. If you look at the zonal mean, you get some slight warming in the low latitudes in the tropics and subtropics. You get this accelerated warming in the Arctic, but now you actually have cooling trends in the mid-latitudes. And the question has been, so I've tried to make the argument that these two are connected, that a lot of, it's very contentious and it's up to debate. Is this just a random, relationship that we have this warming, amplified or accelerated warming in the Arctic and these colder temperatures in the mid-latitudes? Or is there a physical connection? I've tried to argue there is a physical connection. That physical connection will come through the polar vortex. And since I was speaking to you, they want to show one thing here. So here's kind of the Arctic oscillation pattern on the left, top left. Here was the trend. So you can see they have this, and this is only looking at land temperatures from the CRU data set. The Climate Research Unit in the United Kingdom. But you can see you kind of get this similar AO pattern. When you're looking at these trends, this is 1989 to 2008. It's from a paper that came out in 2009 of mine. You can see these cooler trends across northern Eurasia and eastern North America, and very project strongly onto this AO pattern. But since 2000, these are the temperature anomalies since 2009-10. we can see that you still see these colder temperatures in the interior of the continents, but it does not look AO-ish. And certainly, I think some of you guys in Bismarck can appreciate it. So I've been kind of in the center of the continent, not so much the East Coast as it was, a decade earlier. Same thing in Eurasia. So I just bring that up because it's just an interest. I point out just change in the trends is very interesting, but it certainly has a big impact, let's say, in the northern plains there of the U.S. And I don't know if you guys feel this is the case, but certainly here in the northeastern U.S., this, despite the warmth, we've had lots of snow. Here's this index that NOAA puts out. I don't know if you guys are familiar with it. It's focused on the northeastern, and it looks at societal impactful storms. It's called the Nessus Index. So this is Nessus Index. This is Nessus, a number of Nessus storms. They rank it like, I think hurricanes is 1 through 5. 1 is the least impactful, but still, it's disruptive. But and 5 would be the most impactful, just like with the Saffir-Simpson scale. 1 would be the weakest hurricane, 5 would be the strongest. So they have the same thing. Let's just look at the number of these storms. And every decade, and the index that starts from 1958, so and this is through 2 winters ago, but every decade had 8 or less of these Nessus storms per decade. Right? But the most recent decade, we've had 27 altogether, so a tripling of any previous month. Okay, so I'm going to get back to the polar vortex, which maybe is the thing that interests you guys the most. So, and I think there's been really interesting trends going on with the polar vortex. So here's a trend in sea level pressure. I mean, hopefully, as I told you, that Euro blocking, which you can see up here. So this is the sea level pressure that's favorable for weakening the polar vortex, and you see kind of this Euro-Scandinavian blocking. And if you look at the trends in sea level pressure, you can see that there's been this increasing trend in sea level pressure in that same region. And if you look at the polar heat flux, which is really, so here's the area. So here, polar heat flux out of Asia, really disrupts the polar vortex. If you look at the trend of the polar, you can see in those these two main areas of disrupting the polar vortex, you see this increasing trend in the polar heat flux. So it does seem that these recent trends that we've been seeing, both in sea level pressure and the polar heat flux, would lead to more disruptions of the polar vortex. We did this, the polar vortex has really been thought of as binary. It's either weak or strong. I had a feeling that there's more nuance than that. So we did a cluster analysis of the states of the polar, and we came up with 7 different clusters. But cluster 1 really shows a strong vortex. The green is low pressure, so you can see a deeper low. This is a strong vortex, and then it gets weaker as you go up and higher in clusters, and the weakest vortex is cluster 7. Those browns represent, lower, higher pressure over the Arctic. Again, this is the stratosphere, polar stratosphere. So this is the weakest type of vortex. These are really large polar vortex disruptions. If you look at the trends, there's been a decreasing trend in the strong vortices and an increasing trend in the weakest. And you can see not only just cluster 7, but also cluster 6 here as well. So this is through looking at the reanalysis, but really the takeaway is that we have this increasing in the weak stratospheric polar vortex states and a decrease in strong stratospheric polar vortex states. And again, I would argue it's consistent with what we're seeing in these trends in the sea level pressure and in the polar heat flux. And looking at the temperatures associated with these different clusters, so here's the strongest polar vortex cluster, and here's the weakest. You can see the anomalies are really focused in Eurasia. So you can see when you have a strong vortex, you tend to have warmer temperatures across northern Eurasia. You also have warmer temperatures in the eastern U.S. And then when you have a weak vortex, you have cold temperatures across northern Eurasia. You have warm temperatures, let's say, in North American Arctic, and some slight cooling in the eastern U.S., but not a robust signal. The really robust cooling is across northern Eurasia. But if you look at the by weeks, that was like instantaneous temperature response. But if you look further out, this is by weeks, so it's week 1, 2, and 3. You can see that though the temperatures start really cold in Eurasia, over time that you have an increasing in the intensity of the cold across eastern U.S. With time. So even though you may not be cold immediately following the polar vortex eruption, so this analysis suggests over time, about 2 weeks' time, that cold temperatures will make it to the eastern U.S. Now I threw this in the last minute because guys heard really interested in the stratospheric polar vortex. The previous analysis I showed was for 10 hectopascals, right? We duplicated the analysis at 100 hectopascals, and we got a little bit different clusters. Here, but you can see here, you can make out the strong polar vortex as cluster 1, the weakest polar vortex, cluster 5. But this cluster 4 is a little different. So you can see this ridging, high pressure over the North Pacific sector of the Arctic, between Alaska and eastern Siberia, and then this lower pressure across eastern Canada, extending out to the North Atlantic. And here's also the time series. And there's been this kind of increasing trend as well with this cluster 4. And really why, so here's the temperature pattern associated with these different clusters. So, here's cluster 1, the strongest, and that should look familiar from the previous slides. And here's that weakest cluster, again, should look familiar to you with the cold and across northern Eurasian, really focused on northern Asia. But if you look at this cluster 4, the cold now is really focused, a really intense anomaly here in North America, especially in the northwestern part of the continent, with really strong warming now in that North Pacific sector. So very different temperature response to these two different flavors, let's say, of polar vortex disruptions. And again, here's those temperature anomaly differences. But also, if you look at the sea level pressure anomalies, right? So that really strong, that cluster 5, which is the really strongest polar vortex disruptions, you get this kind of canonical North Atlantic or Arctic oscillation pattern, right, with high pressure over the Greenland and Iceland, and low pressure, stretching from the east coast to Portugal. But this cluster 4, you get this more of a West Pacific oscillation with strong ridging across, near Alaska and eastern Siberia, with downstream troughing across, the interior of North America. So it shows you, why this circulation anomaly pattern is consistent with the temperature anomaly pattern. So very different tropospheric response to these two different stratospheric warmings, and this is really something that I think hasn't really been appreciated by the community. I bring this up because we had this really cold, record cold first half of November. So here's just looking at the stratosphere. Just quickly pulled up. You can see that ridging here in the North Pacific sector with this downstream trough, and this is in the stratosphere. But here's the troposphere. Just a forecast, but you can see that the strong ridging center, right, let's say over the Bering Sea with this downstream troughing across eastern North America. And let's pull this off the web very quickly, but we had this really cold temperatures, warm in the west, but really cold east of the Rockies. Maybe centered in the Great Lakes, upper Midwest, but very consistent with what this cluster 4 and everything that I've attributed that this really record cold we had in early November to this cluster 4. So the difference between these two different clusters here is that the heat flux, or this vertical energy transfer, is being absorbed in the polar stratosphere. Here it's being reflected. So you've got so the energy kind of bounces off the polar vortex and comes back down into the stratosphere. So that's why you can very quickly get kind of reflection of what's happening in the stratosphere and the troposphere. These polar vortex disruptions are, again, very impactful for North America, east of the Rockies, but they also tend to be short-lived. Maybe the impact is 1 to 2 weeks, whereas the bigger polar vortex disruptions, the impact could be more like 2 months. So, but this is a much short-lived, but it also tends to be much more intense. And it seems to me they happen quite regularly, almost every winter. We had last fall, here in the East U.S., we had a really very strong cold outbreak around the holiday season, end of December, early January. The gas almost ran out in New England. That was one of these type of events. So, so I just kind of noticed that when you have this pulsating warm in the Arctic, so this is increasing polar cap height. So this is the polar cap height plot. You could think of a proxy for Arctic temperatures, from the stratosphere down to the surface. But when you have like kind of this pulsating warm in the Arctic, you tend to get more extreme weather across the hemisphere, mid-latitudes. So this is at 2019. Here was that reflective event that led to that record cold in the U.S. and that whole thing ended with this bomb cyclone. But then there was this was a reflective and this was an absorptive event, and I've gone through that a little quickly, so hopefully you're kind of catching it. This was a great winter to really show really nice examples of both. But this kind of bigger polar vortex disruption here in February, is from 2 winters ago, really led to cold weather focus in your area, Montana. But then, the kind of extreme weather, winter weather, did move east with time, and we had this 4 consecutive nor'easters. And also, it was in Europe, there was a beast from the east, and they had also cold and snow, cold and snow. But, the point of this slide, it is actually a good example to show both these two different the impacts of the two different flavors of these polar vortex disruptions, but also just to show you that you tend to get these extreme events with when these Arctic pulsates warm. So I did that was a qualitative, I wanted to do a quantitative study. I picked out 12 cities throughout the north and eastern U.S., looked at the relation between polar cap heights and polar cap temperatures and severe winter weather. Luckily for this talk, one of the cities that I did choose was Bismarck. So I'll show some data from Bismarck and how, again, it's been quiet. I've gone, I guess it's over 11:10. If you guys want me to wind this talk down, I can skip, but I do have some targeted analysis for Bismarck. So here's, so anyway, jump in. I haven't heard anything in over an hour. Hopefully I'm not just talking to myself. Here's looking at the relationship between polar cap heights and severe winter weather. So, the temperatures of the heights are in the bottom, go from cold to warm. And then the shading is the severity of winter weather. I've taken this actually from Barbara Mays Bustad, who's, I think in the Oklahoma office, National Weather Service. She came up with this severe winter weather, that's kind of a catch-all, this AWSSI. That, kind of measures how severe a winter season is, using both temperature and snowfall. So the red means it's a very severe winter weather, increased severe winter weather, and blue is less severe winter weather. And you can see for a lot of the cities, and especially in the northern eastern U.S., when the Arctic is cold, you have a decrease in severe winter weather, and when the Arctic is warm, you have a kind of a spike in severe winter weather. And here is pulling out Bismarck, right? So this is what it looks like. So here's all severe winter weather. You can see this relationship holds for Bismarck as well. When the Arctic is cold, you tend to have less severe winter weather. When the Arctic is warm, you have a kind of the spiking in severe winter weather. And I broke it out by temperature and snowfall only. When you look at temperature as well, the relationship holds very strongly. So when the Arctic is cold, Bismarck tends to be warmer. And when the Arctic is warm, Bismarck tends to be colder. The snowfall, the relationship was not that strong as it is for some other cities. But it is stronger for Northeast. I don't think I have Boston here, but you can see it's a better relationship. But it's certainly the cold temperatures and the index as a whole is a very strong relationship. Here's maybe this shows it better. So here's kind of a graph. So this green is the severe winter weather index, and the blue and the reds represent Arctic temperatures. And you have a really nice linear relationship. When the Arctic is cold, Bismarck tends to be warmer in the winter, and when the Arctic is warm, Bismarck tends to be colder. And you can see it really, the severe winter weather really spikes here because it's kind of like off the chart when the Arctic is warmest. And yeah, I wrote Boston, but that meant that was Bismarck. That's not Boston. That's Bismarck. Yeah, so I mean, I think it's very impressive, this relationship between Arctic temperatures and severe winter weather, across the northern and eastern U.S. and certainly including Bismarck. So here's for Boston. I just wanted to show this. So I look at the daily polar cap height and severe winter weather. Everything is a trend, a daily trend. So you can see the Arctic has been warm from December through the end of February. The Arctic has been warming, like throughout the winter season. This is this black line not only represents the zero line for the trend of severe winter weather, but also kind of where the divides the stratosphere and the troposphere. And you can see, though, even though the troposphere is warm throughout the winter, you can see this cooling in the early part of the winter, and then you get these polar vortex disruptions in mid to late winter. And with the severe winter weather index across Boston was either normal, no trend, or a weak, decreasing trend before these polar vortexes, or following these polar vortexes. You can see there's actually an increasing trend in severe winter weather. Now, this is Boston because I wanted to contrast it with Bismarck. The Bismarck, it was not, at least with this analysis, and this is only through 2016. Maybe if I did it through last winter, it would change somewhat. I should probably update this plot. But you can see this. So there is this decrease, prior in severe winter weather leading up to these polar vortex disruptions. Maybe since then, after these polar vortex, so mid to late winter, it kind of gets back to zero, but it doesn't look like Boston. We can clearly see this an increase in severe winter weather. Bismarck did not. But like I said, I think maybe if I included the past two winters, this might look a little different. Here's looking at snowfall return. So the lower the number means the snowfall returns more quickly. So you have 2 inches, 4 inches, all the way up to about 20 inches. So like a look at Washington, the blue represents pre-Arctic amplification, and the green represents post-Arctic amplification, or something like Detroit. That's very clear. The return period for these bigger snowfalls was much less. So you had, let's say you had to wait 10 years for a big snowfall in Detroit before Arctic amplification. After Arctification, the return period is really shortened up. So maybe if it took 10 years, maybe now it's 4 years in Detroit for these bigger snowfalls above a foot. So I think I showed Bismarck here. So that relationship is very clear in some of these eastern cities, as it shows up as well in Bismarck. Maybe these 10 to 14 inch snowfalls are happening a little more frequently in Bismarck than in the period of argument than they previously, but it shows here the very largest snowfalls used to happen more frequently than in the amplification period, though I don't know, maybe if this was updated, maybe through last winter would things change. I do want to talk a little bit about, winter 2018-19. Again, this plot that, I showed earlier showed that strong Euro blocking, Scandinavian blocking that was key to weakening the polar vortex. We had that. This is for 2 months. This is an anomaly. It's very impressive, strong Scandinavian Euro blocking last fall. And if you look at the heat flux from snow cover and compare it to the observed from last week, you can see a very nice match of the timing of the heat flux. Very nice timing, that analysis that I showed earlier in the talk, from looking at snow cover. And looking at the polar cap height, it was almost an identical match in the timing, exactly when this polar vortex disruption took place. Matches the analysis using snow cover. Now the big difference was following the polar vortex disruption, based on this analysis, you expect a strong downward propagation, right, of these polar cap heights or the AO, and that really didn't happen last winter. A little bit here in late January or February, but not nearly as much as you would expect based on historical data. And you can see here's just an animation of the polar vortex from last winter. You can see it start this warming here, and then eventually warming is going to come in the end of the month. That's really going to disrupt the polar vortex. It actually splits into 2 pieces. So one piece over here with Northern Europe, and the other one here with the East Coast. But I think this was important for last winter. You can see that so you have these 2 little vortices. And the North American one really gets, you can see the blues, the cold temperatures in the stratosphere really focus over the interior of the continent, over the just, over the Rockies and the plains of both Canada and the U.S. That really was where the largest temperature anomalies were for the, for the winter last winter. And, so it does seem that eventually where that, that breaking, that split of the polar vortex and where it ended up, there was really cold in the middle of January in the northeast U.S., but then really, we had really that big polar vortex event in January in the Midwest. They got a lot of media attention, but the cold really then lingered where that kind of polar vortex, at least that daughter vortice parked itself. Yeah, so I'm just, often leading up, right? Leading up into a polar vortex, like you get warm temperature across North America. You can see this is leading up to that polar vortex disruption. It takes about 2 weeks for it to propagate. You can see it was really warm. It started out to look like a really warm winter across North America. And this is very consistent from these, again, absorptive events, right? So I talked about reflective and absorptive. And the really strongest polar vortex disruptions are these absorptive events. You can see this is very, so we had a really warm, and maybe you guys in Bismarck are saying, okay, we're going to coast this winter. It was very warm across North America, but then following the polar vortex, you can see, as warm as that was, the cold was even more intense. It really focused over the interior of the continent. So I'm sure you guys want to know about this winter. So snow cover was above normal. Here's the time series. So I did show this earlier. A more busy plot, but here is this past October was over 1 standard deviation above normal, pretty high, 7th highest on record. And then here's that plot I like to show of that Euro blocking, Euro-Scandinavian blocking. That's really key to disrupting the polar vortex. Here's a plot, I sent that on the blog, showing that blocking in that same region for the month of November. This is coming out of CFS as a forecast. This is also, I did a paper looking at polar vortex displacements and splits. But again, it's just the same theme as Euro blocking. Here it looks more like a wave one, right? Strong, high pressure over northwest Eurasia and low pressure in the North Pacific. And I do think the pattern we've been having looks very large amplitude, long wavelength, wave one, which would be more of a displacement. So while the past winters we've had these polar vortex splits, I would think this would be more of a displacement we'll see. Also looking at the temperature here, I correlated Eurasian snow cover with November surface temperatures. You get a cooling east, in Asia and northern Asia, kind of warm here in the northwest of North America. Maybe a hint of cooling in the eastern U.S. But the temperature pattern for November really matches what you expect, how the temperature response would be in November. This is from our latest heat flux, and you see that the heat flux is now getting active, and predicted May more active. It's been a little bit more uncertain today's one than it's been showing the previous one. But anyway, you can see it's gotten more active. I do want to point out, so that early November, disruption of the polar vortex and the cold that followed was really just reflective. And I think one way you can really characterize it in the heat flux is that you get this striation, right? You get the upward heat flux and then a downward heat flux, and it kind of reflects off the polar vortex. So you get this, red and blue striations in the wave activity flux. You see none of that in the predicted heat flux that's coming up. So this looks to be more of an absorptive event. That's a bigger event, and it obviously matches those plots that I showed with the cluster 5. Here's again, just a polar vortex disruption. Polar vortex animation. You can see it's clearly it's been displaced. It's moved towards Eurasia. You can see heating coming around the polar vortex into but it's early. You can see right at the end there, it looks like a much bigger disruption coming. I did think, we have this polar vortex model. We try to predict, when there's a possibility of a polar vortex disruption, and it says, the model definitely says around mid-December is the best probability of a polar vortex disruption, so like around December 15th or so. We'll see if it happens. The model tends to over-predict, so a lot of false positives, I guess you would say. So, but obviously it did, I think, successfully anticipate a disruption of some magnitude, whether it'll get to major warming status, and that's where the winds reverse at 60 north and 10 hectopascal. They go zero, below zero, they go negative, so they go from westerly to easterly. That's defined as a major warming. We'll get to major warming. We're going to have at least a minor warming. I think that looks pretty confident. But the major warming, I think, is an open question. And so here's looking at that polar cap height. You can see here's kind of these tropospheric precursors that we've been having. One last one coming up at the beginning of December, and that should trigger off this polar vortex disruption of unknown magnitude. And you can imagine we'll have, at some point, there'll be this downward propagation. Will it follow, like if we do a historical average, a very robust downward propagation, or one like last year where it was not as robust? I don't know. But this is my last slide, I think. Just, well, maybe the second to last slide. I'm discussing all this on Twitter, but really in depth in my blog. I will have a forecast put out for the Hemisphere in the blog before the end of the month. I'll probably do that as well. Anyway, so I hope everything I discussed here is really what lays the groundwork for the foundation for the blog. Okay, so ENSO-based forecast exceptionally poorly last winter. Statistical, so that's my conclusions. The statistical forecasting uses snow and ice as predictions perform much better. I argued today the pathway of winds of snow cover is through the polar vortex. Researchers have also argued that the signal from Arctic sea ice extent also propagates through the polar vortex. And I think that you can use both of them really to capitalize on the forecast to complement. They're not supplementing, but complementing or replacing a tropical prediction. They can complement. And again, because of and I think they're really important for not only seasonal but even sub-seasonal prediction because of their influence on the behavior of the polar vortex. Climate change is resulting in Arctic amplification, but this is also coupled with decreasing Arctic sea ice and increasing fall snow cover. And heating from sea ice extent retreat and cooling from snow cover advance constructed interferes with the large-scale planetary arrays that are so influential on polar vortex behavior. Now here is, I did put up, this is what our forecast is for now. The temperature forecast I think I'm going to change. I did want to put up, but I will post the official, the one that'll be up there for the, and I'll verify again so it'll come up in the blog at the end of the month. Thank you.
Okay, thank you so much, Judah. That was a really great talk, and I know it kind of.
I'm very relieved to hear your. I'm very relieved to hear your voice.
We've been here. We just kept ourselves muted because people were in and out and things like that.
Okay.
We'll go ahead and open it up to questions. I don't know if anybody. I have a bunch, but I don't want to take over if anybody has any so far. Amber, if you have any, feel free to go type in the little chat box since you don't have your microphone. But Judah, I was just wondering if you could kind of elaborate a little bit on the timing and the confidence of these sudden stratospheric warming events, because what we're really trying to do is add a little bit of value to what we're getting from CPC to help our partners. So I guess if you could just touch on that at all with things that, with the forecasts that are seen, and then how long it can be until we're relatively confident in a sudden stratospheric warming event happening, and then how long, and then how confident are we in a cold getting to the surface, if that makes sense.
Yeah. So, yeah, I mean, I could have given a talk on how the models really struggle with these sudden so there are two types, right? So there's the reflective, which I think is associated with that cold, that cold that we saw in the first half of November. Everything there happens really quick. It's a very quick, short time scale. Everything happens really quickly there. I think the models handle it pretty well. So again, everything it's not a very long-lasting event, and it's not going to, shape, let's say, the winter as a whole. Whereas these larger events, these absorptive events, like we saw last January or 2 winters ago in February, those anomalies, I think the whole thing with the anomalies, they handle poorly. So I think confidence is pretty low throughout. You know, even you know, there was some chatter on Twitter. We're going to have a major warming by late November, early December. Again, our vortex model said it wasn't going to. I didn't think based on the vortex model that was going to happen. And in the blog, I think I talked about mid-December, and I still see that. But you can see that there's just a lot of model mayhem when it comes to these events leading up to it. So I mean, you know, so I mean, the models are all showing some kind of disruption. So I think I feel confident saying there'll be at least a minor warming. But you know, the question is, will there be a major warming? And I think that will be very difficult to know really up to pretty close to the event itself. You know, even in last year we had a pretty large event happening in early January. The models were in disagreement even in late, you know, the last few days of December about what was going to happen. So, and then the whole downward propagation is even more complicated, and the models handle it even worse. In general, they don't have, so, you know, so we watch these events usually in the mid-stratosphere, and then you start this downward propagation. The models will be clueless about what the impacts will be, at least until that signal gets to the tropopause. So I would say don't trust the models until that signal gets to the tropopause, and then once it tends to settle in, the models tend to then finally do well. I mean, you tend to get a kind of a stable pattern, and the models do better. But until that signal hits the tropopause, I would say you really can't trust the models. Okay. Again, historically, when you've gotten these big events, so I mean, I think we're getting a big events, whether it, you know, qualifies as a major warming or not. I'm not as hung up about that as a lot of the community. I think there will be important impacts on our weather, but historically, we take historical averages. You expect maybe the impacts to be first felt across Eurasia, then make their way into the eastern U.S. But the past two winters have showed us that you know, there's no guarantee, and the cold was centered much further west, and we've seen, like, I mean, in 2018 at least, that cold there did make it to the East Coast. Last year, it never really made it. I mean, I don't think you're not as concerned about that in Bismarck, but I have some theories of, about the sea ice maybe changing that. One thing that's been different this year than the past two winters, the sea ice in the Barents Seas has actually been more extensive this past fall than it has been the past two winters. So I think that low sea ice there is really important for anchoring that Euro-Scandinavian blocking, which can really keep that blocking in place long enough to, first of all, lead to a very large disruption, but also I think it tends to favor the cold folks shifted further west across North America. And kind of, if you do I didn't show it here, but if you're doing the kind of analysis between low sea ice in the Barents Seas and temperatures across North America, the cold is more towards your neck of the region, and the East Coast tends to be warm. So I think that played a part the past two winters. Sea ice is more extensive this fall in that region. It's been less extensive and more on the North Pacific side. So I think that's two implications. First, it doesn't seem to be locking in that Euro-Scandinavian blocking as long as it did the past 2 years. So, we are getting that blocking. Will it last long enough to lead to it's there long enough to at least to disrupt the vortex? Will it lead to a major warming? I think that is more questionable this year. I have less confidence in that than the past two winters. But also, the fact that there's less sea ice, I do think maybe the cold might be focused further east from any kind of polar vortex disruption.
Okay. So if we were to see this stratospheric warming event in mid-December, the cold would make its way to the surface by the beginning of January? Is that about the time?
Yeah, so it's about 2 weeks. So right now, our model says December 15th is the best day for it to kind of hit a major warming. So if, let's say it is that week or so, then it takes about 2 weeks. There is an immediate impact. I think there will be an immediate impact. And in my blog, I've discussed there's an immediate impact. It's something that happens right away, but then there's really the long-lasting impact. So, the way it seems to be shaping up, maybe with ridging over Alaska, and troughing, that ridge over Alaska, there could be an immediate impact of ridging along, either in the Gulf of Alaska or right along the west coast. Exactly where it sets up has huge implications where the cold is focused. So that's an important detail. But the long-lasting will be more, will be 2 weeks later. So, yeah, so if there's a kind of an extended period of severe winter weather in North America following a polar vortex disruption, I would look for it to start showing up around the holidays. So,
okay.
Again, yeah.
Yeah, that's good for our messaging, especially with the holidays coming up.
So, I mean, yeah.
One of the questions that Ken and I had when we talked a week or two ago is one of the struggles with the Arctic Oscillation is even if it goes negative, there's always this doubt of where the cold air is going to end up. And you kind of alluded to this earlier in your talk. And I just want to make sure I had this right, is that with time, the cold, even if it doesn't start over North America, that it'll eventually make its way, the cold air that's associated with these events. Is that right?
Yeah, I mean, that's yeah. I mean, the polar vortex, so I think that's more of a polar vortex detail than an Arctic Oscillation detail. But yeah, if you look at the correlation between the Arctic Oscillation and temperatures, that relationship is stronger across Eurasian than it is North America. And like I showed at the very beginning of the talk, the snow cover and the AO hasn't, that relationship is falling apart. I bet, and I didn't look at this, but the relation between the AO and temperatures in North America has also gotten much weaker recently than it has been. I mean, it has not been a good, we had these really cold winters, at least in the eastern U.S., 2013, 14, 14, 15, and the AO was positive both those winters. But, if you looked at the temperature now, I would have thought it was a negative AO. It was positive. So, and it really has not been working out well. Also, the AO hasn't really gone negative since the winter of 2012-13. Mm-hmm. So something strange is happening with the whole AO paradigm, and that's why when I started the blog, I really wanted to focus on the AO, and I've shifted more to the polar vortex because I think that paradigm has worked better in explaining our winter weather and trying to anticipate our winter weather than the AO. Okay. Yeah. I have some theories. I think it maybe has to do with sea ice, and I like to think of this this decrease in, this dramatic loss of sea ice is kind of a climate disruptor, and maybe these old relationships aren't working as well. But even though that AO, again, coming back to the AO snow relationship has not worked well, I think last winter, the reason I showed last winter, one reason I showed last winter, and showing the lead up into this winter is that, that whole snow cover kind of paradigm that I set up has worked really well. And the only reason, I think to anticipate a polar vortex disruption now is because of the high snow cover. You're not going to get it from El Nino. You're not going to get it from the MJO. You're not, even the sea ice, I'd argue, wouldn't get it. Also, the timing is not right for sea ice. But really, the only thing I think that can explain a physical force that can explain the timing of this polar vortex, what we're seeing now, is the snow cover. So.
Okay. My next question, is there a certain month, December, January, February, where it's most common to see these sudden stratospheric warming events? Is there?
Right. Yeah, so January is the month. Okay. Certainly January, February together are the two most, typically they happen in January. I say that's the month it's most likely to happen. The 2 months it's most likely to happen is January and February. So if we get one in December, that would be pretty unusual. It usually doesn't happen that early. Because so that's, again, maybe one reason why I think some skepticism is needed whether we will get we're going to get a minor warming, I think. Mm-hmm. I'd be shocked at this point we don't get a minor warming. But, whether we get a major warming, I think is not a lot high confidence in that. One, because the blocking is not lasting as long as I would have liked to have seen. I do think that the fact that the sea ice is so much lower in the Chukchi, Bering, Beaufort Seas than it is in the Barents-Kara Seas, and so that's the North Pacific sector versus the North Atlantic sector, right? So the past 2 winters we had the sea ice was really lowest in the North Atlantic sector, which really kind of anchors in that blocking, Ural-Scandinavian blocking that's so needed for a polar vortex disruption. This year, it's been on the North Pacific side, which is not as favorable for these large polar vortex disruptions, and you already see that blocking is migrating from the North Atlantic side to the North Pacific side, much quicker than it did the past 2 winters. So, so I think that's one reason, and also the fact that it's happening. You asked me about timing, but also it doesn't usually happen in December. The last time it did happen in December was 2000, December 2000. Okay. Yeah. So that's unusual. If it would happen, it would be pretty unusual.
Okay. I think my last question would just be, what would you recommend we look at just as like a quick sort of tool that we can use? Because that's, a lot of people at the office are maybe not super into climate, so Ken and I are trying to find just quick things that everyone can look at and understand that would maybe help us foresee some of this stuff just a few weeks out.
Right. So, I mean, I try to be as quick as possible on Twitter, on my blog. But I mean, the first sign I'm looking for that polar vortex. I mean, well, let's say first thing I look at is snow cover, of course. When it's high, my antenna will start going up. But I mean, the thing that I'm really looking for is that Ural-Scandinavian blocking, a pattern that matches, and I showed different iterations of it. That's the first thing before anything shows up in the models. If I see that kind of pattern setting up with Ural-Scandinavian blocking, and then especially if it's coupled with lower heights over the North Pacific, that is the most favorable pattern for starting to disrupt the polar vortex. That is so that's when, if I see a pattern like that, I would definitely anticipate some kind of disruption. Will it get to major warming? I don't know, but try to. But that's the first. That's the thing that I can. I mean, obviously the heat, this polar heat transport, or the wave activity flux. That's also that needs to be active. I don't think you're going to get a polar vortex disruption. There was some talk, earlier in the century, early 2000s or the noughts decade, that this stratosphere has its own internal variability. I mean, I've never seen any evidence of that. So I don't think you're going to get a polar vortex disruption without this heat transfer from the troposphere into the stratosphere. So I mean that we compute that every day. But I mean, there are other places now on the web that are showing it as well. Other scientists have started doing the same. But I mean, that typically comes after that signal, either with the sea level pressure or the mid-troposphere. I showed it both the sea level pressure. I focused mostly on sea level pressure, but I mean, I also showed it for mid-troposphere. But that's the first. If I see that, then I usually start sending out the tweets. But that to me. So, but those are again, maybe heading into the season, if I see low Barron's Kara sea ice, high Eurasian snow cover, that's looking for it. Look for that blocking pattern, that Scandinavian Ural blocking, and then looking for the increased polar heat transport. But by the time you're getting that polar heat transport, the model's already starting to show some kind of disruption, right? So it just has to be the physics.